What you have just seen is a geometric interpretation of a concept in calculus called the arc length, and that's what we'll be discussing in this video. Consider a particle A which is initially sitting at the origin of our coordinate plane and eventually tracing out a cycloidal path for the period of, say, 4 seconds. The parametric function r of t defining this curve takes in time as input and spits out a vector with coordinates t minus sine of t and 1 minus cosine of t, representing a point on the curve. So the parametric function maps inputs along the time axis to a point on the plane along the curve. Now the question is, what is the distance traveled by particle A in these 4 seconds? Or in other words, what is the length between the endpoints along this curve? And to help us answer this question, we'll take help from our imaginary, loyal, and mathy friend, whom I'll be addressing as particle B. Particle B travels according to the instructions given to it. For example, if you were to instruct the particle B to travel along a straight line for 4 seconds, such that the distance it travels after t seconds is exactly 0.05 t cubed, particle B does that for you. It is loyal and mathy for a reason. The specific instruction we'll give to particle B in our context is as follows. The distance particle B travels along a straight line in a time t should be the same as that of particle A. Okay, is the instruction clear? Now the issue is, this instruction doesn't make sense because we don't know what distance particle A would travel in a given amount of time. That's the whole thing we are trying to figure out here. But bear with me, everything will make sense in just a few moments. Understanding concepts in calculus often begins with certain assumptions leading to approximate solutions. And then the assumptions are relaxed such that the approximate solution converges to its true value. So let's see if we can make some reasonable assumptions in our case and then refine the assumptions to get closer to reality. The assumption that we'll make here is that the particle A travels not exactly along the curve, but along the secant lines to the curve resting on those points corresponding to the inputs along the time axis that are evenly spread out by a distance delta t equals 1 second. So the particle A travels along these secant lines during each of the delta t durations while abruptly shifting direction every delta t seconds. And notice that these distances need not be the same. Also, each of these little distances, which we'll call delta s, has got two components, delta x and delta y. Applying the Pythagoras theorem, delta s is the square root of sum of squares of these individual components. So, given this secant line assumption and our previous instruction, a loyal friend particle B tries to figure out at what constant velocity it should travel during each of these delta t durations, such that the distances it travels is exactly the same as that of particle A. Velocity is the ratio of distance to time, delta s over delta t. Substituting our previous expression for delta s, the velocity during each of these delta t durations is the square root of delta x over delta t whole squared plus delta y over delta t whole squared. If we were to graph the velocity of particle B as a function of time, it is going to look like this discontinuous step graph. It stays at a constant value for delta t seconds and discontinuously jumps to a different value every delta t seconds. Each of these distances traveled by particle B can be expressed as the product of velocity during that interval times delta t. So, summing up all these little distances can be seen in a whole different perspective as summing up the areas of rectangles on this velocity graph. The width of each of these rectangles is delta t, and the height is given by the velocity during that interval. And if you have done some calculus, you would probably be guessing where this video is heading towards. There'll be a lot going on the screen right now, so you'll have to pay close attention throughout the screen. As we decrease the size of our time step delta t and eventually let it approach 0 in the limit, the secant line assumption gets closer and closer to the actual curve. And that's exactly what we want. And when delta t approaches 0, the ratios delta x over delta t and delta y over delta t are nothing but their respective derivatives x prime of t and y prime of t. Also, the velocity graph of particle B now approaches the graph of this velocity function. And finally, the sum of areas of rectangles under the velocity graph approaches the area under the graph of this velocity function. And that area is just the integral of this velocity function with respect to t. So, the distance traveled, or the arc length, is exactly equal to this integral. Isn't that neat? I'll play the animations once again. Try to relate to the sequence of events happening here.